what I choose to present here is just part of my project at Flensburg University with Professor Peter. It's a little bit different from Sibeli and Elizabeth, but I think it's the first steps before to think about the kitty or classroom activity. So it's about magnetism and the heat conduction in Seebeck's work and how the challenges of this experiment. The main goal of the project is always to address this lack of historical material to use in classrooms. And the last experiments and the last historical case studies that we have worked with, it's about 18th and 19th century, because most of them have a kind of experiment. And my group, they like to do experiments. It's not my expertise. You see here, that's not with me, but they like so. Then we try to do these things, okay? And this case study is about Thomas Seebeck. The first contact that we had with this, it was the translation of the primary source. But really, we realized that the experiment is not easy to do. So we tried to investigate how to do this experiment, and also the impact of Seebeck's work on the academy in 19th century. So I made some questions to this historical case study. Is why was Seebeck doing experiments on magnetism? Which were Seebeck's procedures during the experiments, and how did the contemporary scientific community react to his findings? So in this presentation, I'm going to show the paths for the historical research, because I think it's one of the challenges when the teacher wants to do something with history, and the first thing they ask you is how I can start this work, where is the sources or resources and these things. And I'm going to say something about the biography of Seebeck, the experiment, 2 main experiments, and what I'm thinking about the lesson plan, but I'm honest with you, I depend a lot on my students who are teachers, because I never teach in high school, so I'm always asking them how we can do this, because I don't know how to interact with the students and to promote the inquiry and all the investigative part. So to start this research, I start with the search for biographical resources, and then I used Roberto's recommendation also and went to the catalogs of scientific papers. It's a catalog of all the works from the scientists, because I'd like to know why Seebeck was doing that. So I should know about what he was studying and the others' works. And then Seebeck has 18, there are 4 on the other page, 18 works, most of them in German, was a big challenge. And then I started to look for these works, and I found only 2 that are related with the subject magnetism and electricity. And then I went to the analysis of Seebeck's original works, and which involves the translation and the analysis and many problems with the translation. Big problem I had because of the translation of the German to English and to English to something that I understand in Portuguese. And then I looked for some contemporary studies, because Seebeck cited some names, and these names were important to understand why he was thinking about that. and look for secondary sources. I don't find many works about Seebeck because Seebeck is not so notorious, and most of us only heard about Seebeck's effect, but never about Seebeck. So we don't have many things about him. And the last thing is try to replicate the experiment, which is the big challenge to me. It's terrible, okay? So Thomas Seebeck was most of the time worked most of the time like an independent scholar. Sorry for the mistake there, it's the autocorrection. Because he had this inheritance from the parents, so only in 1819 he got a position in Berlin Academy of Science, but before this year he always worked as an independent scholar. And from 1802 to 1831 he lived in Jena, Bayreuth, Nuremberg and Berlin. And from Jena he got contact with Goethe, Hegel and Weiss. Goethe the writer, Hegel the philosopher, and Weiss the mineralogist. So these three characters were important for Seebeck's work. And in Jena he also knew the nature philosophy, was one of the how can I say, philosophies of that period in Germany, was very important in the beginning of the 19th century. We don't have many things about Seebeck because he only published 10 scientific papers and a small number of brief notes, so nothing so important. And most of his correspondence was lost, excepting with Goethe. And there is a lack of information about his personal life. You can find many articles from his son. I don't remember, I think it's August, about acoustics. And his other son worked with the pedagogical reform in Germany. Okay. His scientific papers are about different subjects, like as study of mineral properties, chemical reactions, polarization of light, and magnetism. Okay. And between 1806 and 1819, he collaborated with Goethe about the theory of colors. But when he got the position at Berlin Academy, he broke with Goethe, and Goethe was important until he got the position. And then after this, he broke this relation. So the main works of Seebeck, I'm going to be fast because I'm always fast and I know everybody here is on hunger, so okay. So the main works of Seebeck, that is I'm trying to replicate and to understand, are from 1821 and 1822. So it is important to know how was the scenario in 1820, because this scenario influenced Seebeck to look for these new relations. So in 1820, there was a belief on the polarity of forces because of the nature philosophy. So Ørsted, influenced by this, Ørsted was one of the scientists that believe in nature philosophy, and Hitler also, and Seebeck knew all these people, met all these people. And in 1820, Ørsted discovered the relationship between electricity and magnetism. And after Ørsted's discovery, he did a long travel for Europe, disseminating his ideas. And reproduce Ørsted experiment and also trying to improve and see better the magnetic phenomena. If I'm saying... So there was a speculation on the nature of the relationship between electricity and magnetism, and there was at least two ideas. The idea of Ørsted was a transversal magnetism, and also the idea of the French research, Ampere and others. And at least two different interpretations to this relationship. And in terms of procedures, there was a belief that experience is a direct and epistemologically primary source of scientific knowledge. So mathematics was not the right idea to explain something, and most of the experiment was just qualitative. No numbers, no formulas, no equations, nothing like this. And, in 1821, Seebeck, in this contest, tried to replicate Ørsted's experiment and tried to understand how the magnetic polarization worked around this circuit. So his first work about this is this one, sobre magnetism, on the magnetism of galvanic current. And the experiment is very simple. His main question was, is the electric tension the only condition for magnetic excitation? And this is, no, it's not there. Not there. So this is a simple pile, galvanic battery. So there is a disc of copper and disc of zinc, and between them a humid paper with chlorhydric acid. And he just closed this and tried to measure the magnetic effect around this circuit. And he got some conclusion about circular polarization. And then he tried to change this circuit. So he made this second one. This is copper, zinc, the paper inside it, and two wires in A and B. And then putting the compass in different places around this circuit, he got that configuration to the magnetic effect. And he understood this like two kind of state of magnetism with two possible states, the plus M and the minus M. So this is a kind of, it's a polarization of magnetism as they believe the polarization of electricity. Okay? It's kind of analogy with things already know. So no quantitative experiments. So his conclusion was that the electric polarization occurs inside the galvanic battery and stimulates the wire's magnetic polarization. The magnetic polarization is an internal modification. So Seebeck believed that the copper wire had a kind of magnetism, a latent magnetism, and the electric polarization stimulates this latent magnetism. But the electric polarization is only inside the battery, not passing through the wire. Okay? And he also concluded that the magnetic tension increases as the electric tension when the number of layers increase here. So it's another battery. And when he was doing this experiment, he notes that the chemical reaction induces the increase of the temperature of one of the layers here. So the temperature in this part is zinc, copper, and layers of copper, zinc, and paper, homemade paper, and he notes that the temperature of zinc increased. And he asked himself if there was some relation between this chemical reaction, electricity, and also the magnetism. So all these ideas of relation between different, they called forces, electric heat and chemical reaction was in the nature philosophy, okay, this idea. So following the experiment, so from this idea that the increase of temperature, he did another experiment. This is the main experiment that we know about Seebeck, and it's a magnetic polarization of metals and minerals and difference of temperature. His main hypothesis is two metals connected can be magnetic without a humid conductor. And this, the date there is important, the year, because see that Seebeck experiment is from 1822, 1821, 22 until 23, but he published only in 25. Okay. So the experiment is this. He has a Schweiger multiplier that is 12 meters of copper tape. This copper tape has 5 millimeters of from large. The large is 5 millimeters, but he didn't say anything about the thickness of this tape, and he didn't say anything about the number of turns, and nothing about the size of the magnet needle inside the multiplier. And in the extremity of the multiplier, you have a disc of copper, a disc of bismuth, and he tried to close this with the hands. Okay, this is the first experiment. Well, this was the first challenge to replicate the material, because he said Schweiger multiplier, but in 1821 we have many kind of multipliers just because of Ørsted. So you have at least 3 different multipliers. Poggendorff and Schweiger, they only describe how could be this multiplier, but we don't have any kind of picture of the multiplier. Okay. Cumming in England, he described how could be this multiplier and draw some pictures of this, but nothing about the length of the wire or how this can be constructed, nothing about this. So these are models from the Smithsonian Institution. And so this is Seebeck. He said that Schweiger has 2 different models, and Schweiger worked with a wire, not a tape. And if you look for Ørsted explanation about Schweiger multiplier, it's very similar to that one. That is the image of the instrument in Galileo Museum. So that one from Galileo Museum is completely different from the description of Schweiger, and I don't know what Seebeck did here. So it was the first challenge. So the experiment is this. He tried to close this, and he notes that with bismuth and antimony and uranium, when he just closed this, copper, bismuth, and copper, the compass needle deflect. Sometimes, depending on the material, the compass deflects to west or to east. And then the first answer, he tried, well, maybe it's deflecting because my hand is humid and this is working as a battery. And there, okay, if this is like a battery, if I put zinc, deflects also. But when he tried to do this using a disc of zinc, there is no deflection of the compass. So it's not working as a battery. And then, oh, okay, but maybe the problem is keeps going my hand. So he tried to do this kind of pressure there using different contacts. Wood, and no deflection. Metal, no deflection. Humid paper, no deflection. So his conclusion is, what is different between wood, metal, and my hand? And he concludes that is the temperature. Okay. I'm not sure when Seebeck was doing this experiment because he said nothing about the temperature, the environment temperature, and his body temperature. Okay, second challenge to replicate this. So if you are here in Brazil, never discover Seebeck effects. No, never in summer, something like that. Okay. When he got this conclusion, so the next step was trying to corroborate, and so he's gonna do many experiments, changing the metals and changing the configuration of the circuits. So that one, it's a bar of bismuth and the copper, and A and B are in different temperature. And then he tried another one. This one is antimony and bismuth and close, and A and B, different temperature. And that one, he changed the position of bismuth and antimony and tried also to identify the deflection of the compass. So his conclusion is that all metals have this latent magnetism, the states of magnetism, and the heat polarizes this magnetism. No electric current here, no electricity, because there is no battery. Okay? So the intensity of the magnetic polarization is inversely proportional to the length of the metal. This conclusion is very similar to Ohm's law to electricity. Not magnetism there. And he concluded also that the combination of different heat or cooled metals, heat metals, produces deflection to east or west. And from this experience, from this finding, he tries to do a kind of magnetic series like the triboelectric series from Volta. So this is Seebeck conclusion. So he tried to combine different metals or minerals, and the main source from metals and minerals was Weiss, the mineralogist from Berlin. And he tried, for example, nickel and bismuth go west, but if I put nickel and cobalt, it's the other direction. It's a big confusion because this is in German. I don't remember west and east. Okay, but it's a large table with all this, and the main conclusion in the end of the paper, Seebeck concluded that this can be a possible explanation to the terrestrial magnetism. So it's a little awkward, but he concluded that, well, first, the terrestrial globe is filled with metals, and the presence of volcans on terrestrial surface means a difference of temperature inside the Earth and on this out also because of the air So the air in the atmosphere has different temperature, and because of this different temperature and the presence of metals, so you have the terrestrial magnetism. So this was just one more explanation about the magnetism. Nothing important. Nobody worried about this. This is not important. However, before Seebeck published this, Ørsted met Seebeck and tried to replicate his experiment. And Ørsted was fluent in Danish, German, English, and French. So he tried to, he met many people and tried to disseminate his ideas. And Ørsted understood Seebeck's experiment as a way to reinforce his own ideas. So he proposed the following thing. He proposed that the heat act as a conductor to the electricity inside the metal. And then it would be possible to create a thermoelectric battery if you put bismuth, copper, bismuth, copper, bismuth, copper, and you keep the extremities, the joint, with different temperatures. So he proposed this, and he published this before Seebeck's work. And now what we know about Seebeck effect is that it's thermoelectric effect. Okay. Well, so what can we do with this? Thinking about science education and thinking about the high school classroom. So one idea, and I need to ask to my teachers and my students because they can give more ideas, is to create a lesson plan that emphasizes the concepts, electricity, magnetism, and heat. So this can be, think about the third year of high school or maybe the second year, and highlight the idea of qualitative experiments, not only to put numbers and try to replicate the values, something like that. And the main question would be, can Seebeck's conclusions be reached from the experiments, only from the experiments? Which are his hidden assumptions to get that conclusion? And so if you are trying to understand this experiment, so the idea is to reproduce the experiment. And this is my tentative to reproduce Seebeck's experiment. So I got a tape, a copper tape, but I got just 1 meter because it's not easy to find 12 meters of this tape. Okay? Seebeck say nothing about the thickness, so the only tape that I got is 1 millimeter thick. So this is not easy to do the turns, and probably is not what Seebeck did, okay, but it was the only one that I got. And then I did these turns here, just 3 turns, and I used a pocket compass, because it was the only one that I had at the moment. And I got bismuth, but it's impossible to get antimony and uranium and things like that, like Seebeck, okay? And I tried to do this only with my fingers, but when I arrived in this part of the project, was summer in Germany, and the temperature of the environment was higher than my temperature. So there is no refrigerator, and there is no air conditioner in the rooms, so forget it. And okay, no works with my hands. So how to establish this difference of temperature? Then I use this small candle. hit the candle, and then try and touch the bismuth. And first I put the copper disc inside the refrigerator. Okay, but this is copper, and my experiment is small. So the thermal equilibrium is fast. So you can, if you will see something, it's fast. Okay. So first time that I did this, and I shit here because I put plastic. That's not the idea. But I tried to isolate the tape using 100% silk and linen, I don't know, but this is from, I think in 19th century was possible to find this material, okay? But I put the plastic here to fix the compass because on the tape it was doing this, a mechanical oscillation, so it didn't work. Well, if I did all these things, and if I, instead the candle, I use a kind of, I don't know the name in English, ferro de soldar, to joint metals, high temperature. Solder, solder. So you can see the needle do something. But the idea is trying to do this with hands. So which variables should I change here to get this phenomenon, this magnetism, no? So the idea is to take these ideas of the challenges and how to change the variables to high school, and thinking about discuss about this and discuss about the variables and all these hypotheses that are necessary. Well, when we try to replicate experiment, and I learned this with Peter, I think technical skills are very important. Expertise with this kind of materials, and also tacit knowledge, how to work all this. And my idea, well, I think I should to increase the number of turns first and try to do this better. But if I increase the number of turns, I need a specific support to do this. And I should know mercenary. This is not my strong ability. Then I ask my student. This is I always asking my student to do something because I don't know how to do it. And my student, who doesn't know about the history, but he knows how to do this. Okay, Gerson, my student in the room. Okay, so Gerson made this for me. So the idea now is trying to simulate this tape, join many wires because I need a contact. Yeah? So a wire is not enough. I need the tape and I need the contact. So using this support here. So some parameters for the lesson plan. So if you are trying to insert this in classroom, to develop this experiment in classroom, how can we do? And the first idea is that the students need a previous knowledge about Ørsted, and because we wouldn't like to use anachronic concepts like the right-hand rules and things like that, and charges and positive charge, negative charge. This is not the idea. Okay. Also, an introduction to the subject from a daily phenomena associating electricity, magnetism, and heat conduction. So I think you can do this thinking about cook something in a copper pen and things like that, or using the thermometer. The digital thermometer is an idea, or all these sensors that are based on temperature and electricity. To design the experiment using available materials without step-by-step script or guide. So this is always the idea of the investigative approach. And use the experiment like an open problem, so we can have many answers to that. To discuss difficulties and possible solutions. There is no only one possible solution or result, so this is important. To promote peer, teacher, students, and students' didactical material interaction, and to explore Seebeck's context and epistemological background through a historical narrative. So the historical narrative should have elements like the experiment qualitative versus quantitative. Also, this version of Seebeck's experiment and Seebeck's version of his own experiment and things like that. The dissemination of science and possible distortions. Many interpretations for the same phenomena. Conditions for or of historical experiments. So to explore or to confirm previous assumptions. And technical skills and text knowledge and experimentation. You know? So this historical case study includes physics concepts and a discussion on the nature of science, but we try not to emphasize the discussion about the nature of science when we do our lesson plans. The replication or reproduction of a historical experiment implies different skills that unfortunately I don't have, but sometimes the students have more skills than I have. This is very common. And if this historical case study is associated with an interactive and inquiry-based lesson plan, and this depends on the teacher who is going to do this, and not only about the issue or the experiment or what we intend to do, it can contribute to science education. So, thank you. It was like this.
Questions? Breno?
Hi, Anna. Thank you for the presentation. Oh, Breno, UEPB. Thank you for the presentation. One quick question. Do you know that there is an experimental kit for university class, university course in physics that studies Seebeck's effect?
I don't know, but if you find something, probably is you have two metals and a battery.
Yeah, no, I'm telling you because
Okay,
there
okay.
is.
Yeah.
And I offered a course on, we call thermal physics at UEPB, and there is an experimental kit. It is produced by a Brazilian company, and the experimental kit is terrible. It's very...
Does it work?
It does not work, and it's very difficult to manage, and the students don't understand because they don't have time to understand, and everything that you said, the metals, and it's hidden. You know, it's like a circuit, and you have like two how can I say that? Two recipients where you. In one of them you put hot water, and in the other cold water, and it's terrible. So one of the things that maybe could enhance your proposal is to see how not to do with this experimental kit, and I can show you and I hope that my colleagues at UEPB do not hear me, but. I can send you the how do I say, the script. No, it's not. Yeah, the report that students should do, and I can send you so you have an example or a counter example.
Now that you said about the recipients, I remember that we have something in Thiago, in the department, the lab from university here. We have this kind of Seebeck, but it's totally, you have no idea what is there. It's just put hot water and cold water, and you see
there's a multimeter, and you see like the changing of the...
But you change the compass or you change the current?
No. You're measuring you have a multimeter, and then you oh my God, how do you say that? I've completely forgot. The change of potential. It's like you see the sign in the multimeter changing when the temperature, like you're adding hot water, and then there is a moment where one of the recipients is in a higher temperature than the other, and then you see that change in the multimeter. That's it. That's the only thing that students see, and they now they do that 100 times, but they do not comprehend the experiment.
Probably they draw a graphic.
Yes.
With temperature and the current and so I think what puzzled me in this experiment, if you look for Seebeck effect on didact book, this is semiconductor. But you don't need to know about semiconductor to explain what is happening here. No, not to explain maybe, but you can understand what is happening, and you can understand the experiment without you know about semiconductor. And usually, what we know about Seebeck effect, it's Ørsted interpretation of Seebeck effect, because it was interesting to have another relation. So now it's not only electricity and magnetism, it's heat, electricity, and magnetism. So this is the idea of nature philosophy. So this is, Ørsted was very good, like dissemination of these meanings, like the Schweiger, but the idea is totally different.
Yeah, but we studied that only in thermal physics. Like it's like a thermal effect. And just a quick comment. This is very new at the university right now. This was the first time that this kit was used, and I hope that you come up with something new, avoiding a tragedy.
Another thing. Okay. Just a suggestion. There's an article written by Ørsted in the Chambers Encyclopedia. He wrote it about 1830, about the effect. I suggest that you have a look at that. It's a big article, but it's big because Ørsted used the opportunity of writing that article to speak about himself. But maybe, I don't remember, I used it just to study Ørsted, not to study Seebeck. But perhaps you can find something interesting there.
Now, I think you must know, there is a book only with the select letters of Ørsted and with the select works of Ørsted. It's in Danish, but also in English.
This article is in English.
Yeah, so
yes.
I think it's the last chapter of this book is about thermoelectricity, and then Ørsted gives some details about how was electricity and since the beginning, and then he used to do this kind of marketing about himself. Yes. Yeah.
Elizabeth primeiro.
Following from Roberto about the importance of the low resistance conductor, and you spoke of having a hard time to find this copper tape. At least in the U.S., it's very common, and we use it in our teaching, and where we get it from is stained glass. The foil, the copper foil, is made and in different widths, and it's used by artists to wrap around their pieces of glass. It has an adhesive on one side. So maybe this is a way that you and your students maybe could get access to inexpensively already made these copper foils.
I found something like this, but with glue. And this thickness from this kind of tape is less than 3 millimeters. So
Yeah,
this
thin.
is too thin.
Too thin. You think it's too thin.
Yeah.
Okay.
But I saw Project Runway, and I saw some, they are trying to do clothes using copper, and they bought this in material things to construction. So the next step is to look for this kind of tape in stores, common stores, because from internet I didn't find anything. I found a company from Portugal, but they only produce this with 1 meter large, and then I need just 5 millimeters, and it's a lot of money just for 5 millimeters. But it's important to cut, because machine in Flensburg is like this, so it's impossible to cut all the hole at the same time.
Yeah.
And if we try to, okay, I have 1 meter, 1 meter, 1 meter, but if I sewed this, so I have a resistance, so I can't have a resistance. So.
And I had another question about the diagram where you showed, I think it was Seebeck's diagram, and it showed multiple, we might call them voltaic units. He uses some other term. It's even before that. It has you called it a stack or layers, and it looked like those voltaic layers were in parallel in the configuration, and yet he's using the term tension, and so there's an interesting inversion there, because we would say that if they were in series they would have a higher tension. So I think that would be interesting to look into, because it highlights the different thinking that he has, even from, I think, his contemporaries there, about what might be going on. I don't know, I'm making this up, but...
Yeah, I think this is part of my problem with the language. Because sometimes when you try to translate, it's not the meaning, and I try to understand in German, and I don't know German to try to understand that in German. So, for example, when I translated this experiment with using the tape, he said, I don't remember, I think he said copper draft, something like this. And the Google Translate like copper wire. Then the first thing that we bought was a wire with 5 millimeters of the diameter. And then my my colleague from there read the things in German and said, no, this is not a wire, this is a tape. So 5 millimeters is the wide it. It's not, not the diameter. So maybe some words from Seebeck. Yeah. In German, they have another meaning. And when we translate, we only translate, you can change the meaning, and maybe you have a misunderstood because of the translation and not because of the Seebeck thought.
Agora, Andrea, por favor.
Andrea do Cefet, and Anna, thank you for the talking. I'm curious because why do you choose this effect, and if this effect, this work, is together on a big project, because I know that you have works in heat, in natural philosophy. So I imagine that it is part of a big project, okay? And so if I'm not wrong, I want to...
Okay, so we had a project, a big project, 3 years ago, and following some recommendations from some conselho, I know, recommendations from Roberto, like a mentor. He said, oh, if you do something, try to do something that you already have, because it's easier, you know. And I knew that in our department, from the university, they have many experiments using electricity and using heat, conduction. So all this project from 2015 was about heat and electricity and magnetism. And so the students come to me and ask, oh, I'd like to work with history. And I say, okay, only if it's 19th century and if it's electricity, magnetism, and heat. Because these things I can put everybody to study together, and I don't need to look for different things. And so in this context, my student was his third year as a researcher with me during the undergraduation. And I said, well, okay, so we are researching about electricity, magnetism, and heat, so let's choose something that is just one subject that it's about all these three things. And then I gave to him this original source to translate in English, first in English and then German. And then he translated this, and he tried to do a kit, a very simple kit with the multimeters and with the metals. And then when I had this opportunity to go to Flensburg, and I said, well, I'm going to Germany, so I think it's convenient that I choose something in German. So, okay, so I start with Seebeck, so let's go with Seebeck. So it's very professional. It's not something from my life. I'd like to know about Seebeck, but very rational. No, I say, okay, Germany, Seebeck is German, and I'm in Germany, so let's go deep in Seebeck. No, but the first idea is because the project was electricity, magnetism, and heat. And this experiment is electricity, magnetism, and heat. So how to do it?
Someone else? More questions? Okay. Thank you, Ana Paula.